It's a great pleasure to be here. I talked with Ali sometime last year, I guess in Canberra, right?
Yes.
And he had the genesis of this idea, and then it's evolved to bring a large number of people from industry and academia together. I think that's a wonderful outcome. So congratulations on pushing that through. For my part, this has been a great experience. I really have not done a lot of work in kind of the traditional area of artificial intelligence. Recently, we've been doing a fair amount of work on kind of data analysis, machine learning types of ideas. And I'll talk about those things a little bit later. But it has been quite a learning experience, just working through what the techniques are and so forth, and exploring that. I'm not going to talk about the techniques for artificial intelligence because that's what the rest of the week's about, right? So for me to sort of go down that path, I would do an inferior job to all of the other presenters anyway, and they will be focusing on the various different methodologies. So I want to spend more time kind of giving a big picture, some of the things that I've learned along the way, and then I'll look at a number of different application areas, and a few of which are work that we've been doing ourselves, and then there's some other things there as well. Now, what to keep in mind that this is a classroom setting, right? So it's meant to be interactive. And I will try and answer the questions to the best of my limited knowledge, but there might well be others in the room who have experiences that can be shared. So if I were to talk for 2 hours straight, we'd all be asleep. I flew in on Saturday, and there's always a few days of kind of unsettled sleep. So if I put myself to sleep, that's not a good outcome. So it would be good, make things more interactive as much as possible. And then I'll certainly break in the middle so we can all stand up, walk around, and talk with the neighbours and stuff like that. Okay, so that's the plan. I found a really nice paper that kind of described or set the context nicely for artificial intelligence, and so I've stolen a few figures out of that, giving the authors some recognition as well, of course. But this first slide kind of points out the progression of sort of industrialization, if you like, of steam engines leading to electric motors, and then really from the time of computation through, there's been this sort of massive change from sort of physical engineering-based developments through more to the computer science, data analysis types of things. What's really sort of been driving economic development in lots of cases is the ability to do fast, ubiquitous computation. So the development of computers in the 70s through to networking later, through to the data analytics, the machine learning, the artificial intelligence ideas that are driving a lot of things. Social media gets a lot of play in terms of the way that the big companies are using the data that they have access to. But it's way bigger than that. And I'll talk a little bit about some of the applications along the way, and I'm sure through this week you'll hear a lot more. But this idea of intelligence, of artificial intelligence, of being able to source lots of information and process that information to make decisions is really what's sort of driving the new economy, if you like. And that's what this figure's showing, the various different ideas. And you'll be getting these slides so you can sort of spend more time dwelling on the details that are in some of these slides. So the evolution of AI, again, I'm not, I don't have a history of working in this field. My kind of connections with this field over the years has been reviewing papers. We all, in academia, we all get way more papers to review than we would want to think about. And what I can observe over the years is sort of the number of papers that have an artificial intelligence aspect to them that have come to me for review. And back in the 90s, there was, well, 90s, maybe it's even going back further than that. Neural networks were new. Various forms of artificial intelligence were new. People were, I think MATLAB developed a toolbox on some of these things. People were grabbing hold of these ideas and trying various different things. And then over time there was sort of a lull in that process, and more recently there's been a great speeding up of that process as well. And in fact, we're adding to the papers these days just to keep everybody, I guess if I've reviewed them over the years, I should be subjecting other people to my stuff as well and making them suffer as well. But anyway, so what do we see if we kind of do a plot of the behavior? There was some early work, the birth of artificial intelligence back in the late 50s. And then things kind of, lots of excitement, but automated theorem proving and stuff like that. But a lot of the ideas didn't push through either from a computational point of view back in those days when computation was quite challenging. Some of the ideas weren't built on rigorous foundations. There was a lull in activity. And then along came the world of expert systems. There was sort of a big deal back in the 80s, and so there was another sort of push into the world of AI at that point. Lots of promises, I can remember, of all sorts of things where artificial intelligence was kind of going to displace the experts through expert systems and so forth, but it didn't quite happen like that, and then there was this downturn again. But I think a lot of the promises that were made back here and didn't quite deliver were computationally bound. And then once computers became faster, then there was this sort of synergistic activity with the computer science people, the machine learning type activities, well, signal processing evolving into image processing, evolving into signal process, machine learning types of ideas. And so the ability to be able to compute really drove the development of theories and algorithms, which drove the development of applications, and there's been this kind of building up exponential increase in activity more recently. So we're sitting down here, there's a lot of different stuff going on. So I live in a Department of Electrical Engineering and Computer Science, and on both sides of the electrical engineering and the computer science, we seem to be hiring an enormous number of people who, at least somewhere in their bio, there's this idea of machine learning or artificial intelligence. It's the way of the future. One of the reasons we keep hiring is that the big companies like Google keep stealing our faculty away from us. And so there's this sort of evolution that goes on, right? But there's a lot of interest, there's a lot of clever things that are being done, and I'm sure there's a lot more that's going to be achieved as well. So that's sort of some background from a timing perspective. Again, all of these figures are not mine. I'll give credit to the authors down here. But it sets the context rather nicely. So the research in AI, there's a whole range of different things that are going on. If we look at machine learning, there's a whole range of different possibilities there. Supervised learning, reinforcement learning, deep learning, and so forth. I'm looking forward to this week of actually learning what some of these learning type techniques mean. And hopefully, well, that's the reason that you're here as well, right? That we can all learn about some of these things. But there's a lot of different algorithms that fit into these various categories that have different nuances. And I think one of the important aspects of a venue like this is understanding what are the right algorithms to apply to the right applications. There's so many algorithms out there, it can be kind of daunting. I know I need to do some kind of machine learning task. What's the right way of doing that? And this week will lead through to that. Okay, and sort of, I guess my last slide in this background is just presenting some of the basis behind the machine learning. And I was interested to read this particular paper in terms of spelling this out into the 5 different aspects of machine learning. And this is a nice table of information between the 5 different forms or background, if you like, and there's the different applications that one can start to explore. So, in terms of the simplest, the knowledge maps are important, knowledge structure, rules, decision trees. If we move to the Bayesian, it's more on the probabilistic reasoning side of things, likelihood of occurrence, those aspects. Moving on, there's the neural network type idea, which is very popular or very useful in machine learning, speech recognition. This Bayesian work is anti-spam algorithms and so forth. So then there's the evolutionary ideas with genetic programming, sort of more on the optimization side, but heuristic optimization that's growing out of that area. And then down the far end, there's the categorization, I guess, where you have support vector types of ideas, filling in missing data. So there's Netflix type systems where you want to be able to do some sparse representation of a whole lot of data and look for patterns within that. I'll talk about some applications that fit into various different categories as we go along. So that's a very brief background into sort of thinking at a high level about the world of artificial intelligence. So to bring it back to power systems, I've really sort of listed a few applications, and the ones that are highlighted in blue I'll talk more about in terms of actual examples later in the talk. So load forecasting has been an important and popular topic for AI type activities for a long time. The neural networks have had success in short-term and longer-term load forecasting. Particularly the shorter-term load forecasting, there's a lot of algorithms that provide very good, high-quality information about load forecasting. Of course, with the growth in the amount of renewable generation, forecasting on the generation side, the renewable generation becomes vitally important as well. Short-term forecasting of wind and solar, enormously valuable from an operational perspective to understanding what the demand is going to be doing, not just understanding what the supply is going to be doing, not just what the demand is going to be doing. And I'll talk a little bit about this, not so much, in the context of clustering ideas used in optimization algorithm, but we will look a little bit at this idea of wind forecast. There are a number of applications in fault diagnosis and condition monitoring that have been proposed and implemented over the years. So fault diagnosis in generators, in transformers, high voltage circuit breakers as well. The condition monitoring aspect where if you take transformers, you're sampling oil on a regular basis, have other information about the transformer, loading conditions and temperature conditions and so forth, and looking for patterns to be able to predict when that transformer, ideally the day before it dies, you want to replace that transformer. So you can get maximum life out of that transformer but not push it too far to the point where you're now dealing with an outage condition. So those types of ideas from a transformer point of view, this condition monitoring and using AI techniques for predicting life expectancy have been found their way into the commercial world. In terms of generator behavior, there's partial discharge measurements that are being used in similar kinds of settings. In power electronic converters, so something that I was reading was looking at the firing capability or the switching within power electronic converters and using artificial intelligence ideas to detect when that switching pattern is not following what it's supposed to be doing. A situation where this is becoming important is where you have multiple, say, solar farms that are electrically rather close. And there's some interesting interactions when the grid is weak, where converters of one solar farm impact or influence converters of another solar farm to the point where you get misfiring between in the converters, and then you end up with that solar farm tripping offline. So detecting protection within the converters, detecting these misfiring situations, there are AI techniques that have been proposed for that area. I'm not so familiar with that world of power electronics to know whether they are actually being implemented by the manufacturers or not, but there's certainly proposals out there for exploring those ideas. Moving on to security and reliability, I'll look at this in the context of doing something different to N-1 reliability. We'll come back to that. But the idea of being able to make decisions using large amounts of data being obtained from across large geographical expanse, and dealing with the differing time delays and the heterogeneity of the data is an important aspect in terms of looking to operating power systems in the future. The idea being that operated power systems forever in a manner where there's a reliance on there being large sources of power, large generators that are dominant across system behavior. And as that changes towards highly distributed sources of generation, lots of wind farms, solar farms, rooftop solar, and so forth, the ability of the operators to be able to synergize the available information in a way that enables them to make decisions, or ultimately that they can make decisions based on information that's being acquired, that's becoming very difficult. And there's a need for the sort of world of artificial intelligence to be able to at least provide information to the operator in a way that is taking in all of those measurements and not just presenting raw information, but presenting enhanced information to the operators. I'll talk later about one form of that, which is the slides that I'll talk about is work that I've done in terms of model predictive control, which is not artificial intelligence in the strictly the usual sense of the word. But I'll use that as a motivation to sort of raise questions about, is there a role, well, I'm sure there is a role between physics-based modeling that underpins things like model predictive control and data-based modeling that comes from the world of artificial intelligence, and bringing those things together to be able to have, in a sense, the best of both worlds. A decision-making capability that's built on the physics of the system, but is enhanced by the massive amount of data that's coming to the system. So we'll talk about that a little bit later. Stability enhancement assessment is another important topic within this world of security and reliability. The way that stability, so if you think sort of large disturbance stability is handled at the moment, it's in terms of running lots of simulations, doing that in an offline setting to understand the kind of capabilities or conditions of the network that give rise to potential stability issues. A lot of offline studies are done to understand what the system looks like under different conditions, and then those offline studies are sort of incorporated into online operator guidance tools of various different forms for different operators. But pretty much underpinning most of the applications that are in practice is the fact that the stability assessment is done under postulated offline conditions rather than under the conditions that exist right now on the system. So the question arises how to best sort of utilize the computational capability that's available in that offline setting, but enhance it with availability of data that's coming in continually, so to refresh those ideas continually and look at ways of being able to come up with better assessment that might not be based on running simulations per se for that particular situation, but based on mappings that have been built in an offline setting through artificial intelligence, and using those mappings to be able to say, hey, the conditions that are existing at the moment are likely to lead to some potential stability problem, and being able to deal with that in a kind of a more complete or a more accurate way. So there's a lot of work there, and Spiros has done some work in that, and I'm sure others have as well. And I think you'll probably talk about some of that work. I'm doing a lot of talking here. There's some more things to come. Any questions, any comments, any thoughts that people would like to share at this point while I rest my voice? Very quiet group. Okay, so we'll move through to the end of the next slide, and then I won't continue beyond that until someone else says something. But we'll get to that. Okay, so identifying cyber and physical attacks, so intrusion detection, ideas, being able to use large amounts of data to determine kind of normal conditions and then look for abnormalities. There's work that's utilizing machine learning capabilities for that kind of situation as well. Electricity markets, determining bidding strategies for energy markets. What's the right way to bid to maximize my income under the conditions of the market as I see it at the moment? But not just at the moment. With the increasing interest in storage, it's being able to make decisions that are appropriate over some finite horizon. So if I own a storage device, I want to make decisions on whether to charge or discharge that device now based on some forecast of behaviour over the foreseeable future. If I make myopic decisions now, using only the information that's available now, I may miss out on some potential opportunity that was going to arise in the future. And so, especially in the world of like storage or devices where there's a temporal coupling, this idea of being able to utilize quality forecasting to make decisions, taking into account what other players in the market are going or likely to be doing, can become quite important. There has been work that's used AI techniques for detecting market power within electricity markets, so situations where one player wields more influence than what you would like them to be able to do. The list kind of goes on a little bit. So over the years there's been a fair amount of work done in feedback controls, so embedding within the feedback control process of generators and motors some artificial intelligence. And I was reading some work. There's some fairly famous people who have done work in that, but from a control theorist point of view, there's still some open issues in terms of how to guarantee robustness of the feedback control loops when you have AI neural nets or whatever the form might be in the feedback process. Having said that, there's some very clever control theorists who are taking ideas from robust control and ideas from artificial intelligence, machine learning, reinforcement learning, and bringing these ideas together. And so, there's work that is moving ahead to be able to produce guarantees on feedback control that is utilizing AI type applications. So there is work out there on generator and motor control, but I really don't know that there's very much of that is implemented in practice. There's work that's been proposed for using AI techniques in the world of voltage regulation, reactive power control. Ideas that have been proposed for using AI in automatic generation control. There's also, so that's at the sort of large grid level, but at the small grid level, so microgrids, where you have this isolated or potentially isolated set of generators and loads, and multi-energy systems where you might have sort of gas supply, solar, wind, electricity, combinations of things. There's ideas that people are utilizing or exploring at least for being able to guide the control of frequency, of voltage within those smaller settings. And I think there's probably more opportunity for making impact at the microgrid level because it's a sort of more closed setting, right? That you're dealing with a small system and it's sort of easier to understand what the capabilities and limitations might be for AI applications in that setting. In the world of feedback controls, two of the things that I will talk about are kind of enhanced technology for enabling feedback control. So I'll talk about this idea of estimating ensemble characteristics, which is, we will get to a bit later, but it's looking at, if I think of a distribution feeder and I want to exercise some control, some demand response over some of the load, let's say the air conditioning load on that distribution feeder, how do I determine how much available load is there, how much controllability is on that feeder? The amount of controllable load is a gain in the feedback control process. And if I don't know whether I've got 100 air conditioners active or 1,000 air conditioners or no air conditioners active, if I don't have that information, then I don't know the gain in my control, and so I can't really tune that control appropriately. And so understanding, being able to extract that information from limited measurements is a machine learning process, and I'll talk about that. And then the other aspect that is sort of similar but not quite is baseline estimation. If I'm exercising some control over loads, how do I know what those loads would have done if I had not exercised the control? So I need to know what the baseline is. If I'm expecting a utility to pay me for a service, how can I prove to that utility that I've actually provided that service if you don't know what my load was going to do if I hadn't provided that service? So again, there's some techniques that we've been exploring that I'll talk about later. At a consumer level, we have a project that is looking at controlling large numbers of residential air conditioners across distribution feeders. And one of the first issues that we faced is that a lot of the houses where we want to control the air conditioners have thermostats that are from Nest, Google Nest. So these are thermostats that learn patterns of behavior within a house, and so they adjust the temperature set point accordingly. So we come along with our applications to make adjustments to the temperature set point, and you already have Google making those adjustments and they're not telling anyone about it. But that's a different story. But the message is that AI is being used in that setting to optimize the air conditioning capabilities or usefulness so that the occupants are happy about the climate, but the energy is being, as minimum energy that's being utilized. So that's just one consumer-based use of artificial intelligence. So I'm going to now open up. So what are other, at the consumer level, what do people think might be other applications, other opportunities for utilizing AI?
Before going to that, can I ask you a question about baseline estimation? If you are doing direct load control, do you think we need the baseline estimation, or we already know it?
So in a sense, that's a philosophical question. So one way of thinking of the controlling loads, large numbers of air conditioners, for example, is to say to the utility, okay, I'm going to drive the total demand of these air conditioners to a constant value. And then if my contract says my ensemble of air conditioners is going to be consuming 3 megawatts of power, any deviation from that is then, so your contract becomes the baseline, and any deviation from that is then penalised. But that's utilising a lot of control effort to achieve this notionally flat outcome. Whereas that might not be the best way of utilising that controllability. It might be that you want some variability, and then when the utility calls for action, you want to deviate from the natural level to some modified level. And then if under that setting, then you've got to know what was the natural level that would have existed had the utility not called for that service. So there's different ways of postulating the problem, but I think in the first case you're utilising a lot of control effort to establish a pseudo baseline, and in the second case you now make available that control effort for satisfying grid needs. But the trade-off is you've got to prove that you can actually satisfy those grid needs.
Sorry, another question, as opposed to actually answering your question. But I noticed that a lot of the applications here, you've got a very much interpolation and short-term focus. On the previous slide, you did mention long-term. So I work in the long-term space where we're trying to forecast and plan for a market in. So I'm wondering just what sort of AI applications can be used in that space?
That's a really good question that I'm going to open up to others. I don't have sufficient familiarity with the different application spaces to really know what would be the right thing to utilise. But can others provide some thoughts on that?
Perhaps maybe I can add something here. So for a long-term forecasting, and first of all, if you borrow something from AI, before that you have to know what are the different factors that have impact on your load. Would it be a long-term thing or a short-term, right? Because I did a lot of work on wind power forecasting, short-term ones. What I realized is that if I have a better understanding of the environment, like what is happening 1 kilometer away from the specific site and things like that, that would be a lot of help. So what are these factors that has an impact on the load consumption in general? And based on that, for instance, we are experiencing very hot summers these days in Australia. That's exactly a factor. If you just assume the historical load from 40 years ago, 30 years ago, 20 years ago, and use any type of AIs to predict the future, you would definitely be wrong, because the temperature is changing and everything is changing in that sense. Or, for instance, you have new technology that maybe reduce the consumption at the load side, new AC technology or something. Again, that has a big impact on your future forecasting. So it's not only the AI itself, but what are the factors that should be considered in your AI algorithm. And that's what I saw, for instance, for battery degradation. Again, the same thing was going on. It's not only having a historical data, but it's more important to know exactly what are the parameters that is affecting the battery lifetime. And then there are probably a bunch of AIs that can help you to get a good estimation of battery degradation.
I think it raises some interesting aspects, like in that kind of what you're proposing, what you're having to explore is influenced a lot by disruptive technologies, and I don't think there's no sort of AI ability to be able to really cope with disruptive technology. In terms of assuming certain regularity about technology development and so forth, then I guess expert system type ideas. A few years back I worked in transmission planning, and the planning process was certainly one that is amenable to sort of expert systems in a sense. But there's also a lot of nuances that can't be captured as well. But projecting ahead is really more about learning the way that experts address certain questions, and then utilising that into the future.
We're sort of using those interpolation models to build an understanding of how the consumer currently behaves. We're holding that consumer behaviour constant, and then we're using scenarios to change the technology and the system in the future. So we're saying the consumer's still the same consumer. They still get hot at anything above, say, 20 degrees, and they still try to search for the ideal comfort zone. The climate is changing by, say, 0.5 degrees over 20 years. So therefore, we change the temperature data that goes into it to account for that climate change. The consumer is still the consumer, and they still want to consume energy, but that energy is now being supplied from behind-the-meter generation. So we use scenarios to then supplement behind-the-meter generation to the future.
Any other comments, questions, or thoughts on this question that I'm posing here?
So, Ian, you've mentioned about air conditioning, and I guess another perhaps major load in the future could be EV charging, discharge. I was wondering maybe you could comment about what opportunities or challenges that you see in terms of artificial intelligence applications for that.
Yeah, there's similarities and there are differences, right? In both cases, there's a demand that you can move in time. But with air conditioners, you can't move it too far, or the temperature deviates by too much, and the occupants are unhappy about that. Whereas electric vehicles, you can move it, but again, there are constraints. So I think, again, it's about if I own an EV, electric vehicle, and I want to make decisions about charging, I need some source of information to be able to make that decision. So in a setting that is a decentralized control setting, actually building into game theory, some work that we did a bunch of years back was to show that if a market or some governing entity provides everyone with a forecast of load or price, and everyone looks at that and goes, all the electric vehicle owners go, this is when it's going to be cheap to charge. I'm going to make, that's what I'm going to charge. And everyone does the same thing, and of course then it's not cheap at all. You get this kind of flocking process. So you need some way of sharing information, but encouraging people to utilize that information in a way that is globally acceptable. And there are challenges that arise from that as well. So again, I'm kind of showing my limited background in artificial intelligence versus more of a background in control, where there are ways of providing damping into the system to encourage EV charging decisions that give everyone a fair share of the available capacity. They're not artificial intelligence processes per se, but I guess in a sense there's some learning capacity that's happening, and then making decisions based on that. There's a lot of talk about if we all had storage, things like I can charge my storage when the price is low and discharge when the price is high. Make money out of the arbitrage. If there's a lot of storage there, then that flattens the price and no one makes money. And then everyone goes bankrupt and you get this boom-bust kind of thing happening. So again, one can think of it in a control setting. I'm sure there's also opportunities to think about that in an AI type of setting as well. So I didn't really answer your question, but there's certainly interesting possibilities there. And by the way, if others feel they have a good answer for any of the questions, feel free to jump in, right? Because everyone has experiences and knowledge that they can share. So think of this as being sort of a group think, the classic AI distributed intelligence idea. Everyone should be contributing if they have something to contribute. If you don't have something to contribute, don't talk.
I suppose that on the consumer side, maybe AI could help boost fraud detection. In many countries, like the utility companies still detect a lot of non-technical losses, such as stealing of energy. And I guess the data analysis on this side could probably boost the detection of frauds.
Very simple AI techniques can be used to detect who's growing marijuana in their basement as well. And that whole privacy issue does come along. Not in our basement, it doesn't, but anyway.
Thank you. Just going back a little bit to that graph that you showed very early on about the kind of cycle that AI has been through. Yeah. I'm wondering if you or anyone else can speak to, we've kind of showing this upward curve, and if there's any risks associated with, what could we run into using AI in power systems that might kind of halt its application and prevent it being this incredibly useful tool, if that makes sense.
Yeah, so I guess the sort of thing that I can see creating issues is things like privacy and the vulnerability that is available when you're sending large amounts of data across open networks. So the advances in AI come about through acquiring lots of data. If that data is coming from a smart meter on individual consumers, it probably only needs one big bad press release, and people go, "No way! I'm switching this whole thing off. I'm feeling vulnerable because of the privacy issues that arise from effectively giving my data away." And then, if the data's not there, then the whole thing falls apart. The other aspect is on the grid side, the telemetry. That is the SCADA telemetry, the information flow across the comms networks for grid operations is treated very seriously in terms of preventing hacking and so forth. But if there's more data that's being brought in, say from a distribution network where there's an assimilation of data and that's being passed on and so forth, and there's an opportunity to be able to hack into that and cause problems in the data stream, then people won't be able to trust that data stream anymore. And then again, if the source of information is not available, then there's no AI application that can made to work. So, for me, the vulnerability I see is that there's a lot more points of potential influence that become available. The more information that's being acquired, the more opportunity to influence that. And that influence can lead to a negative outcome through public pressure. Okay. So don't be too worried about that we're running way behind schedule. I don't have to go through all the slides. I'm not going to make you sit here beyond coffee time or whatever. Okay, so power system data, it's kind of just what we've been talking about. Vast numbers of participants create vast amount of highly distributed data. It's heterogeneous and it has multiple forms, has multiple timescales. It's asynchronous. There's different data arriving at different timing. There's uncertainty, noise. It's incomplete data, so you might be relying on some stream of data and suddenly you lose that. What do? You can't just have your feedback control mechanism stop working. So what happens with incomplete data? And the other thing is, if you think of value density, what's the value of each piece of data? It's very small. It's only when you aggregate that data that you start to see some value coming from it. So if I go to a consumer and say, hey, we will pay you something for access to your data, typically the amount that they would want, it's not worth it to get that data. So of course then you have all the app type things where you sign that away without even knowing what you've just signed away. But each piece of information is quite of low value by itself. There are difficulties in collecting, storing, processing, mining the data. And then, as I've mentioned previously, there are privacy concerns with the data as well. Okay, so I wanted to move into looking at some case studies. We'll look at reliability assessment, and then I think we'll take a short break after that. But these are the various different case studies that I will look at. So reliability assessment we'll deal with. We'll then look at baseline estimation, estimating ensemble characteristics, cluster-based chance-constrained optimization. In all those cases, the machine learning is about acquiring information, large amounts of information, and using that information in a way to assess baseline, to determine what the availability of control is with air conditioners on a distribution feeder, etc. In the final case, where I will look at corrective model predictive control, it's not actually an artificial intelligence type of technology. It's a competing technology. But as I mentioned earlier, the general idea is, hey, maybe we can use some of these physics-based ideas of predictive control together with the data ideas that come out of AI to enhance the capabilities, and we'll look at that a little bit. The notes on reliability assessment are based on notes that Louis Winkel from Liège in Belgium made available. And so he's an absolute expert in this area, and I'm not, so I'm very happy to talk about what he has made available. So, in terms of reliability assessment, what's the requirement? We have, at a sub-second temporal resolution, to balance generation, consumption, and storage whilst satisfying network constraints, despite the threats that come from contingencies or from adversaries and so forth. So what are the threats? Unanticipated variation of generation and or demand, weather conditions that are unexpected, component failures, human errors, adversarial attacks. All of these are possibilities, and so we need to be operating the power system to be able to deal with all of those things. Problems that we want to avoid component overloads, we want to avoid voltage and frequency excursions that are of a substantial nature. And of course we want to avoid cascading overloads or instabilities that lead to blackouts. What we would desirably want is to be able to optimize this power system in close to real time. So that's the sort of operational setting that faces utilities. What's the role for AI in being able to deal with all of that? So one way of being able to do that is thinking about this particular setting, that every 5 minutes or so for the real-time system state, so think of what is the system characteristics at this point in time. We want to assess the risk induced by contingency. So we can organise that information. So based on the data and the models, we have a set of contingencies and the probabilities or the likelihood of that contingency occurring. And then there's this quantity that's the measure of the severity of that contingency. So of a particular contingency at a particular state. So we can assess the expected impact of possible contingencies by summing over the set of contingencies appropriate at a particular system state, weighting the probability times the severity, and get a measure of the risk that is associated with our current operating state. So the expected cost of service interruptions. And then from a probabilistic point of view, again, summing over the set of contingencies that are appropriate or possible under this current system state, we can look at what's the probability of large interruptions by exploring the cases where this measure is greater than some parameter that we set. Okay, so that's kind of, that's maybe not formalized, but that's the operational paradigm that operators are thinking through. Given my current system state, what are credible contingencies and what's the risk associated with those contingencies? So from a machine learning point of view, there's benefits in that evaluating this function here is often computationally expensive. So it might be a power flow computation, or it might be a whole simulation of the dynamics of the power system given a particular postulated fault condition. but it's expensive to repeat that computation. But if we can, if we have to repeat it, let's store that information away and build up a data set which is telling us for particular system states and particular contingencies, what's the cost, if you like, associated with that. And if I store that enough, if I repeat that process enough times over enough system states and enough contingencies, then I build a meaningful data set that I can use to build some approximations. So what I would like is to be able to build this sort of input-output relationship where instead of having to repeat that whole computation, I can just say, here are the traits of interest, this is the likelihood of a risk associated with that. Here's certain conditions that exist on my system right now, and that my mapping, my approximate mapping that's coming out of building this function H says that is likely to incur a risk or not likely to incur a risk. So from my sample of input-output pairs, we build a function that makes the difference between the function output and this y as small as possible on average. So that the details, I'm not going to go into lots of details, but the details are in building that function H, and there's different ways of doing that. Applications learn a regression proxy that says, hey, instead of evaluating this function all the time, let me use this process up here to find this proxy such that if I specify my current state and a contingency, that proxy gives me a good approximate value for that cost. And then likewise, from a classification point of view, this is just saying, again, based on building a function up here, given my current state and contingency, is that likely to lead to a problem of sufficient size or not? So these proxies build from that and allow us a much faster way of being able to assess the likelihood of some issue arising, some contingency causing problems. So the underlying assumption is that these H proxies are faster to evaluate than the actual original cost function, and that it's possible to learn sufficiently accurate proxies. Many real power systems have unusual behavior under kind of rare event conditions. Building these types of proxies under those rare conditions is very difficult because you just don't have sufficient information. The data set is not sufficiently rich to be able to establish this H type of mapping. So the devil is in the details of these assumptions of, do I have sufficient information to be able to build good proxies, and does the computation involved in that proxy, is that actually, do I gain something by computing the proxy rather than just computing the original value? So that's the sort of machine learning setting. And to make the whole process work, one needs to sort of think through the questions of how often should I be updating these proxies? If I've built a set of proxies, should they be updated hourly, daily, monthly? Should they be updated in real time, ahead of time? What's the right way of thinking about that process? How do I gather the data sets for building, for learning the proxies? Do I wait for the actual system to kind of explore the space of possibilities? So using data that's coming from the energy management system that's showing what's actually happening on the real system, or do I use Monte Carlo approaches to give an improved coverage of the space of possibilities, but from a modelling perspective, when I'm using Monte Carlo, I'm then relying on models of the system to generate the information for the data sets which are used in developing the proxies. So this becomes model-based, whereas this is data generated. It's actual, what's happening on the actual system being used. How to best use the available machine learning techniques. What do I want to get out of building those proxies? Do I want to be able to maximize their interpretability? You know, I look at the numbers and I can interpret what's going on and I can make decisions based on that. Or do I want to provide maximum computational performance? You know, what's the best form of machine learning technique? And then how to use the proxies. There's the two proxies that we have, regression proxy and the classifier. Can they be best used in unison? Should they be used in terms of cooperation with other quantities as well? So there's a range of considerations that one needs to think through there. So in kind of presenting this possibility of machine learning in an operations environment, I'm not answering anyone's questions, just kind of putting out, here's the possibilities. Now, how do we explore those possibilities? And I'm sure through this week, there will be sufficient information to be able to kind of more fully explore those possibilities. Okay, so the next thing I wanted to talk about was baseline estimation, but I think it's a good time to take 10 minutes break so people can kind of stretch a little bit and I can get my voice back.